Today's lecture is on section 6.4, I believe. It's like the world's shortest section of a book. And it has to do with how to solve systems of linear equations. So we want to build up to this problem of you have students living in a suite, and one student makes coffee. How long is it going to take the other students to smell the coffee? And so that's the problem we're going to build up to. But before we get to the problem of rooms connected to one another, I want to start with a warm-up problem, which just has to do with a tank of liquid, which has an input and an output. And we need to understand this problem because if we're going to have rooms connected to each other through air vents, each room's going to have an input, each room's going to have an output. So before we can link them together, we'd better understand just what a room with an input and output does. So I want to start with this problem that I sent around yesterday. It's a classic problem. So you have a tank of liquid. So this is salt water. And at time 0, we have 5 grams per liter of salt. So we have a tank with 5 grams per liter of salt. And up until time 0, that's what we have. But there are there's an input and there's an output with a little knob. And we assume that at time 0, both knobs are opened. So we go from having a system which has no flow to a system which has flow out and flow in. So at time greater than 0, so these are closed at first. At time greater than 0, these are open. So it's open. And we now have a flow in and out of the tank. So we're going to imagine that this flow, the outflow, is at 1 liter per minute. And the inflow is at 1 liter per minute. So before we talk about what's flowing in and what's flowing out, if we start with a tank that has, how much water did I assume? 100 liters. So we start with 100 liters of salt water. If the inflow matches the outflow, how much liquid will be in here at any given time? 100 liters. So this is going to be 100 liters, and that's because the inflow rate is equal to the outflow. If the inflow rate were larger than the outflow rate, then the volume of liquid would increase in time and it would eventually run over. If the outflow rate were greater than the inflow rate, the volume of liquid would decrease in time and would eventually empty. But we're assuming the inflow rate equals the outflow rate. And then the question is, what's flowing in and what's flowing out? So what's flowing in is pure water. Here we have salty water. And what's flowing out is salty water. Now, as time passes, more and more pure water will have come in. So however salty the water was in the beginning, as time passes, the water in here should become less and less salty. So the more time passes, the more pure water has come in, the more salt will have flown out, because you start with only so many saltwater particles in the water. So in reality, okay, it's calculus, don't think about finite numbers of salt particles. As time passes, this water will become less and less salty. And so you expect, as time goes to infinity, the salt in the tank should go to what? 0. Okay. So you don't need calculus to tell you that. But our question is, given at any moment in time, how much salt is in the tank? So at time t, how much salt is in the tank? So this means we need some function so that we can plug t into the function. Next question might be, how much salt is there at time t is 100 minutes? Next question might be how to adjust the flow rate so that at t equals 100, you have 2 grams per liter in the tank. All right, so these are all perfectly respectable questions. We just need to somehow figure out a function which will give us the amount of salt in the tank at any moment in time. Once we know that, we'll be able to certainly answer this. If we were smart enough to figure out that function, we'll probably be smart enough to figure out how to adjust the flow rate. So the big question is, how do we get a function that tells us how much salt is in the tank at any given time? So this is going to involve writing down a differential equation. So you've seen all sorts of equations in your life. X squared minus 1 equals 0 is an equation, and its solutions are numbers, specifically x equals 1 and x equals minus 1. That's an equation. A differential equation is an equation whose solution is a function So for example, dx dt equals t equals 3x of t. This is an equation. It's an equation which involves a function and the derivative of the function. Its solution is not going to be a number. Its solution is not going to be a vector. Its solution is going to be a function. We are seeking a specific function that satisfies that differential equation. So you could ask, is x of t equals t squared a solution? So that would boil down to whether dx dt, which is 2t, whether that equals 3 times x of t, which would be 3t squared. Well, certainly there are moments in time where this will be true. It's true when t is equal to 0, and it's true when t is equal to 2/3, but you want it to be true for all t, true for all time. No. And is x of t equals cosine t a solution? Dx dt, well, if x is cosine of t, then dx dt is minus sine of t. And we want to know whether that equals 3 times x of t. So that would be 3 times cosine of t. So 3 times x of t, which is 3 times cosine of t. And yes, there are infinitely many moments in time when this will equal this, but it's not true for all time. So we're seeking, stop it. Okay, just, we seek a function for which that is true, and x of t is any constant e to the 3t is a solution. dx dt for this particular function would be 3c e to the 3t. We want to know if that equals 3 times x of t, which is 3 times x of t is c e to the 3t. Okay, so we frequently model physical processes using differential equations. And once we have found a differential equation, we then try to find a solution. So we're going to look for a differential equation that describes our saltwater tank. And so let's go ahead and do that. Because then we need to solve it. So S of t is the number of grams of salt in the tank at time t. That's what we're trying to solve for. ds dt is going to equal the rate at which salt flows in minus the rate at which salt flows out. This is simply conservation of mass. If the salt is changing in the tank, it's because salt came in and because salt came out. In this case, salt doesn't come in, but this is true in general. This is just conservation of mass. So all we need if we want to write down a differential equation for the amount of salt is we need to figure out the rate at which salt flows in and the rate at which salt flows out. So step one, the rate at which salt flows in. What is the rate at which salt is flowing in? 0, because it's pure water. Okay, 2. Rate at which salt flows out. Okay, so this is a little bit harder. So first of all, I'm going to assume that my water mixes perfectly. So I'm going to imagine there's some big propeller in here. God, I need to learn how to draw. A stirrer. And the thing is stirred perfectly and instantly, and that however salty the water is here, it's the same as the saltiness of the water here, is the same as the saltiness of the water here, is the same as the saltiness of the water here. I'm assuming that the water is perfectly mixed. In reality, the water here will be slightly less salty. The liquid here will be slightly more salty, partly because salt water is denser than sweet water, and partly because you've got the pure water coming in here. So of course that's going to be less salty. But we're going to imagine that the saltiness is the same everywhere. So we just need to figure out how it's going out right here. So we know the outflow rate is whatever it was, 1 gram, 1 liter per minute. And so the rate at which salt flows out is going to be the current amount of salt times the volume times the outflow rate times the 1 liter per minute. So that is S of t. My volume, I imagined, was 100 liters, I believe. 100 liters times 1 liter per minute. So that is 1 over 100 S of t grams per minute. All right. So now I put my differential equation together. ds dt is equal to 0 minus 1 over 100 S of t. And my units are grams per minute. My initial condition, I need to say what the initial amount of salt was. I assumed that initially there were 5. Oh, okay. I was told that the initial concentration is 5 grams per liter. I need the initial amount, which is S of 0, which is in terms of grams. So I need 5 grams per liter times the volume, which is 100 liters, is 500 grams. So this is the problem I need to solve. So the solution of that is going to be S of t is 500 e to the minus t over 100. I can check. First of all, it satisfies the differential equation. I did that example right up there. And I can check that S at 0 is 500 e to the minus 0 over 100 is 500. So I've answered the first question. At time t, there are 500 times e to the minus t over 100 grams of salt in the tank. Now the next question was how much salt was there at time 100. After 100 minutes, there are 500 e to the minus 100 over 100, which is 500 e to the minus 1, which is okay, it's some number. And we were asked what is the concentration. So this is grams. The concentration is 500 e to the minus 1 over 100, which is 5 e to the minus 1, which is approximately 1.84 grams per liter. So we've answered 2 questions. One question was, what's the concentration? So this was the answer to how much salt there was, is 500 grams of salt. 500 times e to the minus 1 grams of salt. The concentration is this. The third question was, how would you adjust the flow rate so that the concentration at time 100 is 2 grams per liter? So looking at this, am I going to need to increase or decrease my flow rate? If my goal is to choose a flow rate so that the concentration at time 100 is 2 grams per liter. Decrease. So from this, I realize I'm going to need to decrease my flow rate. Okay, so I'm going to introduce R, which is the flow rate. Before, R was 1 liter per minute. Now it's R liters per minute. I go back to my equation, and I get ds dt is equal to 0 minus the current amount of salt divided by the volume of liquid times the flow rate. So ds dt is minus r over 100 times s of t grams per minute. And again, I'm still going to want that the initial amount of salt is 500 grams. So I solve this, and I get that s of t is 500 e to the minus r over 100 t. And so the concentration at time 100, I take that and I plug in time is equal to 100. So I plug in time is equal to 100. Those cancel. I get e to the minus r. I have to divide by the volume of the tank. So this is grams per liter. I want this to equal 2 grams per liter. Is that an equation you can solve? Yeah. You put everything over to the other side, and you take logarithms, and you solve for it. And you end up with r being the natural logarithm of 5 over 2, which is approximately 0.92 liters per minute. Okay, are there questions? With all of these word problems, yes.
I'm sorry, could you explain in a little more detail how you got from finding the derivative to getting the function?
Oh, haha. The answer is because it works.
Okay.
When you take your differential equations course in your second year, you will learn how to find the solution. For the moment, you just have to accept that any equation which is of the form, any differential equation which is of the form, the derivative is proportional to the function. Any equation which is of that form will have an exponential solution. So this is something that you were expected to have memorized from high school. How you would find that if you didn't, how would you find that solution if you didn't actually know it or it wasn't given to you, is in your second year math course. Math 294 if you're a material science student. I don't know what the Civ course is. So if all you had was this differential equation, how would you find the exponential solution is a 5-minute argument, but I'm not going to give it here. At this point, you're just supposed to accept it. Other questions? Okay, so let's get to the coffee problem. All right, so the coffee problem is what happens if you connect tanks to each other. So here we have 2 rooms. This is the kitchen. This is the lounge. The kitchen is connected to the lounge by a fan, and the lounge is connected to the kitchen by a fan. We will imagine that these are the only places where air can come in and out of the room. Obviously, this is impossible because the people would die, but let's just imagine. The air entering from under door cracks and through windows will be sufficient to keep them alive, but is small enough that it's not going to be able to compete with the airflow due to the fans. So in here, we have a student who's just made coffee. And here we have a student who's asleep because they've been studying. So at time 0, let's imagine there's 10 milligrams of coffee in the air in the kitchen. Because whenever you smell something, it's because molecules have entered your nose. If you smell coffee, there are coffee molecules in the air. And there are no milligrams of coffee in the lounge. So at time 0, that's where you are. The fans are turned on. Coffee molecules begin to go into the lounge. Uncaffeinated air comes from the lounge to the kitchen. So this kitchen is going to smell less and less coffee-like. This lounge is going to smell more and more coffee-like. As time goes to infinity, how many milligrams of coffee should be in the kitchen, and how many milligrams of coffee should be in the lounge? 50-50. Good. And so the puzzle is, okay, the student in the lounge will wake when there are 20 milligrams of coffee in the air. And that's because her nose activates at 20 divided by 10,000 milligrams per liter. So the kitchen volume is equal to the lounge volume is equal to 10,000 liters. And when the concentration is high enough, particles will actually make their way into her nose to her receptors, the brain will trigger, and she'll wake. So the question is, when does the student wake? Wake up. Further questions would be, if you wanted to have her wake up at a certain time, how would you adjust the fan speed? If you wanted her to wake up at a certain time, how does it depend on the size of the room? Obviously, if she's in a huge, huge room, the concentration is going to be low. Maybe she's not even going to wake up due to the coffee. Then we have the analogous questions. We could have 3 rooms. Here we would initially have 100 milligrams, no milligrams, no milligrams. We would have sleeping student, sleeping student. And the question would be, when does she wake? And when does she wake? Obviously, for this one, as time goes to infinity, the concentration will go to 100 divided by 3 milligrams, 1 over 10,000 liters. We can have 4 rooms, and so on and so forth. Just intuitively, who do you think is going to wake first, this student or that student? Who should wake first, the middle student or the right student? Middle student. They're closer to the kitchen. And we can do 4 rooms and 5 rooms and 6 rooms and so forth. At some point, if you have too many rooms, you suspect that the students might not wake at all due to a coffee trigger. They will wake due to normal triggers. So that would be another question, which is how many rooms, if you have a lot of rooms, will the students actually wake due to the coffee trigger? Okay, so how do we model this? So let's do this problem. So x1 of t is the amount, or milligrams of coffee in the kitchen air. X2 of t is milligrams of coffee in the lounge air. dx1 dt is going to equal inflow from lounge minus outflow from kitchen. So how the amount of coffee in the kitchen changes in time? Well, you're going to have some coffee coming in from the lounge, and you're going to have other coffee leaving from the kitchen. So the inflow from the lounge, we have x2 milligrams of coffee in the lounge. The lounge is 10,000 liters. And then we have the flow rate. And the flow rate was assumed to be some number, 20 liters per minute. So the inflow from the lounge, you have the amount of coffee in the lounge air divided by the volume of the lounge times the flow rate. So that's the flow in that upward arcing tube. You're losing coffee from the kitchen, and that has to do with the amount of coffee in the kitchen, which is x1 milligrams, divided by the volume of the kitchen, which is 10,000 liters, times the rate the air is leaving the kitchen, which is 20 liters per minute. So this gives us dx1 dt is equal to minus 1 over 500 times x1 of t plus 1 over 500 x2 of t. The rate with which the coffee in the kitchen air changes is loss of coffee from the kitchen due to outflow, gain of coffee from the lounge due to inflow. dx2 dt is going to be inflow from kitchen minus outflow from lounge. The inflow from the kitchen is we have x1 of t. This is the number of milligrams in the kitchen. We have the volume of the kitchen. We have the flow rate from the kitchen. The outflow from the lounge, well, we have x2 milligrams in the lounge air. The volume of the lounge is 10,000 liters. We have 20 liters per minute outflow. This gives us dx2 dt is equal to 1 over 500 x1 of t minus 1 over 500 x2 of t. So we're in this situation where we need to solve a coupled linear system. It's coupled because x1, how x1 changes depends on x1 and x2. How x2 changes depends on both x1 and x2. The two unknowns are actually, they're handcuffed together. It's coupled. It's linear because you don't have cosine of x1 of t or square root of x2 of t or anything. dx1 dt is minus 1 over 500 x1 of t plus 1 over 500 x2 of t. dx2 dt is 1 over 500 x1 of t minus 1 over 500 x2 of t. And we're trying to solve that with, what's the initial amount of coffee in the kitchen? I've already forgotten. What was it? How much? 100 milligrams. And the original amount of coffee in the lounge? 0. So here we have ddt of x1 of t, x2 of t is equal to minus 1 over 500 plus 1 over 500, 1 over 500 minus 1 over 500 times x1 of t, x2 of t. This is dx dt equals a times x. To solve this, first, find eigenvalues of a. Second, find eigenvectors of a. Third, write down general solution. Fourth, apply initial conditions. So let me do that. So okay. So when you compute the eigenvalues, you're computing the determinant of a minus lambda I, and you end up with lambda times lambda plus 2 over 500. So that tells us we have one eigenvalue which is lambda 0 and another eigenvalue which is minus 2 over 500. When we look for the eigenvectors, we have to solve two linear algebra problems. And we get that lambda 1 equals 0 has eigenvector 1, 1. And lambda 2, which is minus 2 over 500, has eigenvector 1, minus 1. The general solution will be anything of the form c1 e to the 0t times 1, 1 plus c2 e to the minus 2 over 500t times 1 minus 1. I need to convince you that this actually works, that it will always work. For the moment, you just take the eigenvalue, you put it in the exponential, you multiply by the eigenvector. Eigenvalue into the exponential, multiply by the eigenvector. Now we need to satisfy the initial condition. So the initial condition is that the vector at time 0 should be 100, 0. That was the initial condition. I plug t equals 0 in right here, and I get c1 times 1, 1 plus c2 times 1 minus 1. So this means I need to solve 1, 1, 1 minus 1 times c1, c2 equals 100, 0. I will be able to do that. This is an invertible matrix. It has a non-zero determinant. For sure, it will be invertible because these are eigenvectors with different eigenvalues. I get C1 is 50, C2 is 50. So this means my solution, x of t, which is x1 of t, x2 of t, is equal to 50 times 1, 1 plus 50 e to the minus 2 over 500 t times 1 minus 1. So the amount of coffee in the kitchen is 50 plus 50 e to the minus 2 over 500 t. And the amount of coffee in the lounge is 50 minus 50 e to the minus 2 over 500 t. As time goes to infinity, what does this go to? 50. As time goes to infinity, what does this go to? 50. At time equals 0, what does this equal? 100. Plug t equals 0 in, you get 50 plus 50. At time equals 0, what does this equal? 0. This decreases to 50 from 100. This increases to 50 from 100. So we have 50 milligrams. There's the kitchen concentration. There's the lounge concentration. And here is wake-up time. So time, milligrams. OK, so let me do a MATLAB demo, just because you never see MATLAB in this class. OK, so I took I wrote a little script called Smell the Coffee and Wake Up. It has one input, which is the number of rooms. I set the flow rate. I set the size of the room. I build the matrix, which I have to find the eigenvalues for. I set a maximum time that I want to look at the solutions up to. I compute the eigenvalues and eigenvectors of my matrix. I solve for the coefficients. That's done right here. I construct the solution, and then I plot it. So I will put this on the blackboard. It's a very, very simple program. I believe there are faster ways of doing it, but that's not helpful to you. So if I have 2 rooms, what? Line 78, column 22. Line 78, column 2, extra comma. This is what happens when you make last-minute editing changes. Okay. So here is the kitchen, the number of milligrams in the kitchen. Here are the number of milligrams in the lounge. Here is the wake-up amount. Here's the long time limit. Here is the wake-up time. So if I wanted to find the wake-up time, I can actually, it's an equation I can solve easily when there are only 2 rooms. I can easily solve the equation. Now if I have 3 rooms, here life gets interesting. I still compute eigenvalues, I still compute eigenvectors. Kitchen concentration, lounge concentration, bedroom concentration. The student in the lounge is going to wake sooner than the student in the bedroom. And the long time limit has gone down to 33 to 3 over to 100 divided by 3 grams of coffee. You see there's this overshoot. That's because the solutions involve sines and cosines. And that has to do with having complex eigenvalues. If I have 4 rooms, I see that all 3 students wake up. The further you are from the kitchen, the longer it takes you to wake up. 5 rooms. It crosses barely. 6 rooms, and so forth. So you can add more and more rooms, and you get a busier and busier graph. Ultimately, you just want to see, so here the wake-up amount is the green line. The long time limit is the red line. I should do a longer final time. Okay, you'll play with it on your own. Anyway, I just wanted you to see that systems of linear equations are cool and useful. Solving them is very routine, and the book explains how to do that.